Hello, this is the 11th in a series of relatively short videos that I'm doing about real analysis proofs. For the last 8 videos, we looked at proving fundamental inequalities, including the triangle inequality and the Cauchy-Schwarz inequality. In this video, we're starting a new subseries about what's called the completeness property of the real number system and its consequences. This is part 1. The completeness property, which I'm not going to state right now, is what distinguishes the real number system from, for example, the rational number system. It's kind of a difficult thing. It's going to take a while to really get this if you start from scratch. So I think it's best to start off with some examples. Examples of what are called least upper bounds of sets, also known as suprema of those sets. So we're going to start in kind of a general setting. We're going to assume that we've got an ordered set, S, and a subset of S. What does it mean for S to be an ordered set? It means two things. Given two elements in S, X and Y, either there's an ordering relationship on S that satisfies these properties. Either X is less than Y, or X equals Y, or Y is less than X. They are comparable with respect to this ordering. This is called a total order. It's not a partial order. Partial orders are situations where, given two elements, they're not necessarily comparable with respect to the ordering. But with total orders, which is what ordered sets are, we are going to assume this is true. And there's also a transitivity property. If X and Y and Z are three elements of S, with, say, X less than Y and Y less than Z, then X must also be less than Z, a transitivity property. So that's what an ordered set is. Now you can make pretty much any set that you want, have an ordering on it, and become an ordered set. For example, finite sets, the set of rationals, the set of reals. Even the complex numbers can have an ordering on them. You might want to look that up. Maybe look up lexicographic order as one example. However, not all those orderings, at least for the field examples, like the rationals, reals, and complex numbers, respect the field property, so to speak. I'm not going to say what that means. The concept of an ordered field requires other properties. But initially here we don't have to talk about ordered fields, even though the real numbers system does form an ordered field. All right, some definitions. We say that A is bounded above in the set S, that's assumed, if there exists an element of S such that for, little a is less than or equal to that element for all little a in capital A, and in such a situation, capital M is called an upper bound of A. Now again, this is more general than just the real number system, but for the sake of understanding this as well as you can, and also applying it to the real number system, we can go ahead and imagine these definitions in terms of the real number line. We could imagine S is the real number line, the set of real numbers, and by drawing a line you are sort of assuming in your mind and ordering from left to right. Something is less than something else if the first thing is to the left of the other thing. And we could imagine A here as being lots of different kinds of examples. You could imagine it to be a finite set. Maybe that's A. You could imagine it to be these 4 points plus maybe an interval that is maybe even going off to minus infinity forever here. Such a set A would be bounded above. There would be an upper bound. And in fact, if this is your set, anything to the right of this point, like there, or even including the point itself, would work for capital M. Okay, capital M would be an upper bound of that set A that's in green there. So think about more examples to help you understand what this means. All right, but there are special kinds of upper bounds that we want to talk about now. If in addition to A being bounded above, there exists a beta in S with two properties. One, beta is an upper bound of this set A that is bounded above. And in addition, beta is the smallest upper bound, meaning if you have some other element of S that's also an upper bound of A, then beta must be less than or equal to that other element. So beta is the smallest upper bound of A. We say that beta is the least upper bound or supremum of A. And we write beta equals sup A. And so those words, least upper bound, supremum, and even the abbreviation sup, all mean the same thing. They all mean an upper bound that is the smallest possible upper bound. Any other upper bound of A is greater than or equal to the least upper bound. The least upper bound is less than or equal to any other upper bound. Before we go on and do our two proofs, proof of property 1 and proof of property 2 here that you see, excuse me, I think it probably would be worthwhile to focus a little bit more on condition B that must hold for a supremum. It is an if-then statement, and hopefully you remember from logic that the contrapositive statement of any if-then statement is equivalent to the original if-then statement. So if this if-then statement is true in a given situation for a certain beta and a certain set A, then its contrapositive would also be true. And if you prove the contrapositive, you've also proved this statement in a specific example. The assumption that, excuse me, that gamma is an element of S is kind of a background assumption. So let's go ahead and write, suppose gamma is in S, just like before. We are working in S. What is the contrapositive statement of what's left? What's left is if gamma is an upper bound of A, then beta is less than or equal to gamma. The contrapositive statement would be if the opposite of this one's true, if beta is bigger than gamma, that would be the opposite of beta being less than or equal to gamma, its negation, then gamma is not an upper bound of A. And sometimes this is easier to prove it. In fact, in proof 2, it's going to be easier to prove it this way. And gamma is not an upper bound of A. Anything less than the supremum, anything less than the least upper bound of A, is not an upper bound of A. I think it's probably worth being a little extra careful here and saying what this means. So there exists an element of A that is bigger than gamma, since gamma is not an upper bound of A, such that ST means such that X is bigger than gamma, or gamma is less than X. Okay? So for proof 2, again, that's what we're going to end up proving to show ultimately that, if you look at number 2 here, that B is the supremum, the least upper bound of A. All right, but let's look at 1 first. Here we are in an arbitrary situation. S is an arbitrary ordered set. A is a subset of S that is finite. Okay, it's a finite set. Let's say it's got n elements and that these are the distinct elements. Certainly, in an ordered setting, without loss of generality, you can go ahead, because these are arbitrary symbols anyway, and assume A1 is less than A2 is less than A3, etc., is ultimately less than AN. WLOG means without loss of generality. Because these are arbitrary symbols, that's the reason we can certainly say that. Go ahead and make that assumption. Making AN the largest element of capital A, the goal is to prove that AN is the supremum of capital A, sup of A. All right, let's go ahead and do that. Down here. 2 things to prove again. Prove that AN is an upper bound of A, and prove that any other upper bound must be greater than or equal to AN. AN must be less than or equal to that any other upper bound. And these are pretty easy to prove. This is a pretty easy proof. Certainly, it's an upper bound. Okay, by definition, if you think about it, certainly AI is less than or equal to AN for all of these i's. I going from 1 to n. It's a strict less than if I is 1 through n minus 1, and it's a less than or equal to because it's really an equal to when I equals n. So AN is an upper bound of A. By the way, just a little comment here. It's tempting in this situation to just say AN is an upper bound. But you should always say with respect to what set you're talking about. So it's an upper bound of A. Don't give in to the temptation of just saying it's an upper bound. Hopefully I will not make the same mistake. Now we prove condition B, and that's not too hard either. So suppose you've got some element of S, gamma, and gamma is an upper bound of A. This finite set consisting of A1 through AN, well, that implies, by definition of what it means to be an upper bound of a set, that AI is less than or equal to gamma for all I going from 1 to n, including I equals n. Therefore, AN is less than or equal to gamma, and therefore we've proved the two conditions we need to prove. AN is an upper bound of capital A, and any other upper bound satisfies the condition that AN is less than or equal to that other upper bound. Therefore, AN is the sup of A. And we're done. By the way, it's probably worth me making the comment that a sup of a set is unique. I did say the sup of A. Proving that a supremum is unique is not too hard either. If you assume there were two suprema of a set capital A, call them beta and gamma. Thinking about this contrapositive up here, where without loss of generality beta is greater than gamma, this condition would imply that gamma is not an upper bound of A, which would contradict the fact that gamma is a supremum. Gamma would be an upper bound of A. So you get a contradiction pretty quickly to the assumption that there are two distinct suprema. So a supremum of a set is unique if it exists. Some set don't have suprema, I should also probably mention. I'll let you think about that. All right, property 2. I'm going to assume A is a subset of R in property 2, so R is going to be what S is here. I'm going to assume it's a special kind of subset. It's a non-empty interval of one of these forms. And as far as the proof goes, I'm just going to do, for the sake of time, just do one of these. The other ones are just slight modifications. Let's do the last one. Let's assume A is this non-empty open interval. By the way, the fact that I'm assuming this interval is non-empty would implicitly imply that A is less than B. Okay, by the fact that that's non-empty. I am going to cheat here, you might say. I'm going to use an assumption, under the assumption that there exists a real number strictly between any two distinct real numbers. Now, technically speaking, that assumption requires the completeness axiom, completeness property, I should say. Sometimes it's an axiom, sometimes it's a theorem, depending on your approach. That requires the completeness property to prove, okay? And I haven't said what the completeness property is. It's related to suprema of sets, but I haven't said what it is. So in that sense, I'm going to cheat, but I think it's okay because this is just for the sake of illustration. Illustrating this fact, I go ahead and assume this essentially as an axiom almost, okay? I want to prove that the right endpoint of the interval is the suprema. Okay, and that would be true no matter what kind of interval it is, and whether or not the right endpoint is part of the interval. You know, the right endpoint is part of this interval and this one, but it's not part of this interval and that interval. So suprema may or may not be in the set if the supremum exists. In the first case, when the set is finite, it is an element of the set, but in this situation, it may or may not be. Okay, it's still the supremum in any of those situations. As an alternative approach to using this assumption, I could alternatively consider these intervals to be subsets of the rationals Q, Q standing for quotient. So consider these to be non-empty intervals of rational numbers, no irrational numbers in them. And use another fact that you could prove, that the average of two distinct rational numbers, the rational numbers forming an ordered field, is a rational number between them. But I'm not going to go into the details of how you actually prove that. That would be an alternative approach. But let's go ahead and use the approach that I'm talking about here, where A is a non-empty interval like this, where these are real intervals, including irrational numbers in them. So let's go ahead and think about proving property 2 in the case where A is an open interval from A to B, non-empty, which by definition is the set of all real numbers satisfying the condition that those real numbers are strictly between A and B. Intervals do exist for ordered sets besides these, but in order to use this assumption, I am going to assume that S is the real number system R and A is a subset of R, an interval in R, non-empty. All right. Once again, showing that the thing you want to show is the supremum is an upper bound of the set is trivial. I could say certainly, I could say clearly. Clearly, B is an upper bound of A. I mean, when things are clear, you often can get away with saying clearly. If you felt like you needed to give a reason, I'll go ahead and put a reason in parentheses here. You could say since given X in the open interval from A to B that's non-empty, this means by definition of what this open interval is, X is less than B, so X is also less than or equal to B, and that would mean that B is an upper bound of the set A because X is an arbitrary element of A. But it is pretty much clear here. The second condition is a little trickier, not too bad. Condition B here, though I'm going to use it in the form of the contrapositive. I'm going to assume I've got another element, gamma, that is less than B. B is going to be my sup playing the role of beta up here, and show that that other element is not an upper bound of A, and I'm going to need this assumption here. So suppose gamma is some other element of S, which is the real number system, and suppose gamma is strictly less than B, this thing that we're trying to show is the sup. My goal is to show that gamma is not an upper bound of capital A. And there's two cases you can consider. Case one, suppose gamma is less than little a. Then it's pretty obvious that there exists something in capital A bigger than gamma and also, of course, less than B. In fact, every element of capital A is greater than gamma. And let me go ahead and just write that out in words. You don't have to say every element, you just need to show there exists at least one element. But every element, every one of the infinitely many elements is bigger than gamma. And every element or number of A or in A is greater than gamma. So gamma is not an upper bound of A. Being kind of wordy here. Maybe this is a run-on sentence. You, in doing your proof, would want to split this up into a few different sentences, I think. Case 2, which is a little trickier and requires our assumption that we're making. Suppose A is less than or equal to gamma. Gamma is greater than or equal to A. I am still assuming gamma is less than B, so I can go ahead and also write less than B. By this assumption up here, by the assumption that we made that between any two distinct real numbers, there's another real number between them. In fact, you could even say there's infinitely many real numbers between them. We can say that there exists a real number x such that gamma is less than x is less than b, and I can also put the a back in there. A is less than or equal to gamma is less than x is less than b. But this means, by definition of capital A up here, that x must actually be in A. But this implies that x is in capital A with, once again, this condition holding, gamma is less than x is less than b. So gamma is, once again, not an upper bound of capital A. Therefore, the sup of capital A equals B, and we are done. QED. We verified the two conditions for B to be a supremum up here for this set. And again, just slight modifications of this argument would work for these other kinds of intervals. As a final thing I should do is it's worth noting that there are dual concepts. If you don't know what a dual concept is, you might want to look it up. Of a set being bounded below, an element being a lower bound of the set, and an element being the greatest lower bound, or infimum. I say infimum. I think some people say infimum, but I like infimum better. Of a set written, say, alpha equals inf of A, where alpha is the element that you're talking about that is the greatest lower bound of a set that is bounded below for a set A. Okay? Sups and infs don't have to exist for certain sets. Again, you should think about that too. But this is, I think, a nice introduction to the subject.